Hello there, we're going to continue with the How to Make a Programming Language series. We're going to get back to Nearley.js. This episode is going to talk about a specific feature of Nearley.js which allows you to plug in a custom tokenizer, which is sometimes also called a lexer. And this is their page which explains how to do that. So tokenizers, aka lexers. I mentioned the name lexers even though they say tokenizers in the documentation, because you might hear the term lexer from other sources that you're researching. Actually, it does use the word lexical information here. So I'm just gonna use these two words interchangeably, and you should understand them as such. Now, what is a tokenizer? So a tokenizer is a program that takes your string input. Let's say this was your program. Oh, I have the double quotes here and on the inside. Let's forget that happened. So let's say this is your string input, and we were gonna write a parser to make sense of this program. Currently, we're just having the parser look at every character of this string one after another. So, for example, in Nearly.js, if you wrote the string literal if, then it'll basically, if it's looking at this part of the string at the moment, it'll basically do a match between what is at the current location of the parser, and the rule is trying to define, it'll try to match it up and sort of come up with the matches directly in string format. That's okay. However, it's not quite as efficient as it could be, and traditionally people who are making parsers, they actually use a two-phase process. So the input before getting into the parser would actually go through a box called the lexer, aka tokenizer, and then the input out of the lexer would be a stream of tokens, and then the token stream in turn would get handed off to the parser. So thus far we sort of omitted the lexer part, but in this episode we're gonna bring it back. And the reason we're gonna bring it back is because it helps, mostly because it helps with the performance of the parser. There's a few other benefits of using a lexer, which I will cover, but before that I'm gonna perhaps paint a slightly better picture of what a lexer does. So what the lexer does is goes through this input stream one character at a time, and it's gonna chop it up into these things called tokens, which are just bits of this string, but with a little additional lexical information in them. So basically, out from this string, we would get something like a token for the if keyword, another token for the left paren, and then another one for the n, etc., etc. But each one of these are not simply strings, because each one of these are actually tokens. They contain additional information such as the line number, even column number, and what type of thing is, which is in this case it's a keyword. If the if word is a keyword, and for the left paren you also get a line number, column number, and the type of this might just be called left paren, and so forth. So contained within each of these tokens is some additional metadata about each bit of string. which the parser can then actually make good use of. And because these strings have been chunked, such as like this identifier print has been chunked into one piece, the parser doesn't have to deal with the individual characters, and that is also one reason why this helps with the parsing performance. Okay, so that is the lexer. That is at least what the lexer is conceptually. And now let's look at an actual lexer. One thing that Nearley.js helps us with here is it actually recommends an implementation of a lexer, so that you don't even have to write your own lexer. You only have to configure the lexer, not write it yourself. And the one that it recommends is called Moo, which is also written in JavaScript, with which you can configure a lexer very easily using syntax like this. Whenever you're learning something new and it's integrated with another thing, I feel like it's harder to get at the heart of what something is. So what I'm gonna do first is actually take this Moo library by itself and play around with it and show you how it works. And then after that, we're gonna integrate it with Nearly.js. So let's go ahead and do that. The first thing I'm gonna do is take this initial code example that Moo.js. I love the theme of this project, by the way. We should probably npm install Moo.js. There it is. And then we're gonna make a new JavaScript file. I'm gonna call it mooplay. And then we're gonna drop this code example directly from their README page in here. So this first part of this example configures a lexer. I'll talk about what these things mean. And then once you have an instance of a lexer, which is what that guy is, you can call lexer reset and give it a string, and this would be your input string. Okay, so this line passes this input string, while 10 cows moo, to the lexer. And then after that, what you do with the lexer is you call .next on it. And each time you call .next, the next method will return you a token, which is an object basically. And it should look something like this. Let's try this. That didn't do anything because we didn't actually console.log the return value of .next. So let's try that again. So now you can see we have printed to the screen 4 objects. Each one is a representation of the token, and each one has a type. So the type of the first one, this while word, is a keyword. So and you can also see that there's line number information. So there's a line number and a column number. The line breaks, I believe, is telling you how many line breaks are within this piece of string, which for this one there's 0. Offset is the character offset from the very beginning of the input. So in this case is 0, but for the next one that's 5, because this is WS stands for white space. And I'll show you where these types are coming from. Well, basically they're coming from this configuration object. And you can see the offset of this white space from the beginning is 5 here because of this while word. And now at this point you can probably connect the dots and realize that the type of each token is determined by this key of this dictionary in this configuration dictionary. On the right hand side of each one of these key value pairs is either a regular expression like that, or a array like that, which is sort of like a regular expression that ORs each one of these together. So perhaps you could have written that alternatively like that as a regular expression if you wished. there's some additional syntax if you need more configuration options for each one of these. So whenever you need more configuration options, in this case they need it for line breaks. So basically the documentation of Moo says whenever you're planning to match line breaks with one of these matcher rules, you have to set line breaks to true to tell it that you're intending to match line breaks. And this is a case when that is. So whenever you do that, you need to expand this value to an object, put the matcher in here, keyed by the word match, and then add the additional options there. So that's basically that. Let me show you a slightly simpler example. This time I'm going to use the example from here, from the Nearley.js page. I'm just going to copy this and overwrite this previous example. And the input I'm going to give it is I have 3 cows. Looking at this configuration, I can see that it matches numbers, it matches words, which are any number of characters between A and Z, lowercase. There's also a times. I'm gonna ignore that one. So I'm just gonna write the sentence, I have 3 cows, and I'm gonna expect a number and 3 words and some white spaces perhaps. And actually what you can do with the lexer is you can keep asking for tokens by calling next until next returns a undefined or a null, I don't know which one, and then that's what signals the end of the token stream. Okay, so if I did this and ran it, so now we get to see all of the tokens. So this looks like what I expected. So first I have a word I, then a white space, that's this one here, and then I have a word have, white space, and then I have a number 3 and a white space, and then a word cows. Okay, that's how the lexer, aka tokenizer, works more or less. Moo has actually quite a bit of features, and I'm not going to cover all of them, but I do want to cover one of them, which is the value transform, which they documented here. So as you can see, each one of these token objects has both a text and a value. The text represents the exact string that was matched, that represents this token, and then the value is normally the exact same value as text unless you decide to transform it to something else. And the way you can do that is by using a value transformer. So you can basically say, I actually, for numbers, for example, that's a perfect candidate. For numbers, I actually want to represent the value of the number token as the actual numeric value of that number. So the way you would do that is first take this matcher here and wrap it inside this object and put it inside the property named match. And then the value transformer should be named value, and then the value of value, the value of value should be a function that takes a string and returns something, and in this case, number. So this number function conveniently will parse a string that presumably is a number. So yeah, so if we had done that, then this number token here, its value will become an actual JavaScript number. Let's see that happen. Yeah, and there it is. So this number token has the value of 3, which is no longer quoted, which tells me that it's actually a number. So now the next step is I'm actually going to convert this arithmetic example that we have, which we've been walking through in the previous episodes. I'm going to convert that to use a tokenizer. And previously, the Nearley parser was written in a way using either regular expression matchers or string literal matchers like that. Okay, and now we're gonna instead have this parser plug in this lexer into it, and then whenever matchers like this are written, it's actually gonna match based on this token of streams that the lexer has given you. But how does that work? But the way you actually match the tokens, there's actually two ways. One is you can match it based on the type of the token, which is that guy. You can say, I want to match a new line. If you want to do that, you put a ampersand in front of the type name. Another way of matching a token is by matching the literal string. So which actually looks just like before. So in the cases where we had these literal strings that were matching strings, we could actually, in a lot of cases, leave it like this, and it would still work as long as the text value of the token matches up with that string literal exactly. And I actually think that works with regular expressions as well. So if you had a regular expression that matched up with the text field of the token, I believe that also works, even though it doesn't say that in the documentation. So we're gonna go ahead and give that a try. But the first thing I'm gonna do is write or configure a lexer so that it can handle the arithmetic syntax that we have so far. And that arithmetic syntax so far has things like these. So we can do additions, we can do a function call for simple built-in functions. We can do multiply and divide using this very pretty multiply and the division symbols. And we can have parentheses here. So what we're gonna need to do is sort of break this up into tokens. All right, so I'm gonna actually cut this up in here. White spaces are actually tokens as well. Okay, so that's a lot of cuts. So basically here we have, I'm gonna say we have a left paren. This is a number. This is a white space. This is a plus. That's a white space again, and so forth, etc., etc. So each of the, this is how I'm gonna cut up this input string into tokens. Let's do that. So I'm gonna go to this file and change this configure object to do what I want, basically. Okay, so I have the left paren and right paren, which is gonna, then these are gonna be string literal matches. We're gonna tell Moo, the lexer library, to, whenever it sees a left paren, make a token with the type of L paren. The time symbol and the divide symbol and the plus and minus symbols. And then I'm gonna, for all the function names, for the built-in function names, I'm gonna make them string literal matches. And if any of these 6 names are matched, it's gonna generate a token with the type of built-in function. So let's try that. Just try to execute this lexer by itself first before actually integrating it with Nearley.js. Okay, so there it is. We put in 1 plus 2, so we get a token, a number token with the value 1, and then some white space, and then a plus token, and then some white space and a number token with the value of 2. So that looks great. Let's try another example, a more complicated one. So okay, so this one we got an L paren token for the left parenthesis, and then we got a number with a value 1, and then a white space, a plus token, white space, a number 2, and then a right paren, white space again, a times token, white space again, and then a built-in function, and then a left paren, and then a number and a right paren again. One thing I want to mention though is at Tokenizer, it doesn't do the higher level syntax matching, which means that at this point you can actually give the lexer something that's syntactically invalid, such as like we forgot to close the paren, but the lexer is actually none the wiser about this. So if I do moo play here, the lexer, from the lexer's perspective, there's no error here because it doesn't do the higher level validation. So now let's try to actually integrate the lexer into Nearly.js. So this is what you do. You make a special block like this. It's similar to one of these blocks where you put in custom JavaScript, except this is a top level JavaScript block, which you're asking Nearly.js to put at the top, sort of like a global place of the resulting JavaScript file. And in this case, you're gonna need to put an @ sign in front of this block. Okay, so at this point, you can declare you need to require the Moo library and then declare a lexer like that. And then you need to tell Nearly.js which global variable has your lexer been initialized in using this @lexer syntax. So this @lexer syntax is a special syntax, and then the next word lexer is referring to the global variable that you have set up. So which is to say that you could choose to name that something different, like, I don't know, foobar. And if you've done that, you would change that here. So now we have the lexer set up, but I expect this is not the end of this work. I expect something will not work properly. But let's just run it though, in any case, and see what happens. So we're going to regenerate the parser, and regenerating the parser actually caused the JavaScript version of the parser to update with all of this new stuff. So now let's just try to run the parser again and see what happens. And when we run this parser file, it parses this input, which has been hard-coded here as an example, and it runs through the parser. The parser generates an AST tree, abstract syntax tree, and saves it into this ast.json file. So let's take a look at what's in that file right now. Before, it looked like this, and afterwards we got a lot more information. So you can see this shape with the line number information and the offset and the text and the value. That's a token that's coming from the Moo.js based tokenizer. So something is working. If we take a closer look at this, the operation part of the AST, it has these tokens in them, but the numbers don't appear to have the Moo tokens in them, and we need to fix that. And the reason the numbers are not working, I believe, the way that this math arithmetic grammar has been defined, it does this low-level parsing of the numbers, which it does not need to do anymore. What we've actually done is taken over the parsing of the number part using the lexer, using Moo.js, and it actually ends up being a lot simpler code to write this way. Actually, it doesn't handle decimal points though, although we're not using decimal points at the moment. But in any case, we're gonna switch over to basically handling the parsing of the number using Moo.js, using like a regular expression here, to simplify the definition of the grammar itself. So after Moo.js is done processing, it will already give me number type tokens, and I'm just gonna plug that in. And this digit and digits symbol, it's only used for this number symbol. So I'm gonna actually get rid of all of this code, reference the number token. Remember this percent symbol. The percent symbol is used to tell Nearly that I want to match the token of type number. So regenerate the parser, running it. Okay, running it, and we're getting these number tokens, except they've been wrapped inside of this extra array, which we don't want, but that's quite easy to fix. We just use this this ID function, which is a convenience function provided by Nearly, as we've covered in the previous episodes. So now we should have these numbers unwrapped. So left hand side is a number token and the right hand side is a number token, and that's good. The next thing we can convert over is the white space. So the white space, we no longer need to use a regular expression to do it, because there's a regular expression in the Moo lexer to do that for us. So we can just convert this to point to the white space type. And I just realized I made a mistake here earlier by writing capital WS instead of lowercase ws. It took me some debugging time to figure this out. But when I figured this out, this parser is working just like before. So let's test this. Get the AST after it's generated. So yeah, the white space tokens should actually not make it into here at all, because we're not interested in that information in the AST. But what is beneficial now with this information? Well, there's two main things, in my opinion, about using a lexer that's beneficial. One is the performance enhancement when you're working with large programs, large program with a lot of symbols in it. Lexer can work faster, can do the lower level stuff faster. So we can speed up the parser that way. But a second benefit that we get, really, and this is very important to me, is we get this line number information, so that when there are errors, whether it's a syntax checker error, or it's a program semantic checker, or it's a linter checker, whatever kind of error you want to display to the user, you can actually attach with that error the location that originated that error, and that is extremely helpful for the usability of your parser. Okay, I'm gonna stop this video here. Thank you for watching. If you're following along with these videos and you're working on implementing your own parser, and you have questions or run into issues, by all means you can ask me questions by writing a YouTube comment. Thank you for watching, and I hope you see you soon.